Swayam Prabha. Digital India. Educated India.
Right. So this returns yes or no. This returns a Boolean value of yes or no. Fine. How does one return the graph? How does one return a graph if there is one? Right. So the way to return a graph, right, is actually to return here, right, a pointer to the is to return a pointer to the adjacency matrix, right? Fine. And we will just modify, right? If n greater than or equal to 0, right, we will just modify this sentence in the following way, right? If n greater than 1, let G, sorry, M is the adjacency matrix of graphic D2 minus 1 to D1 minus 1 comma Dn, right? Then construct M prime by adding a row and a column. Right? So you have M here. Right? So you add a new row for the new vertex, right? And you add a new column for the new vertex. Now you write the statements where this obviously you can put a 0 because there are no self loops, and this vertex, right, will be adjacent to all the other, the first D1 minus 1 vertices. First D1 vertices, put a 1 here, put a 1 here, put a 1 here, right, and keep the matrix symmetric, right. So just ensure that appropriate places you put a 1 in this column, right. Construct M prime by adding a row and a 1, right, and zeros and ones in M prime to represent the added D1 edges. Okay. and then you return m prime. Right? So therefore, this code is simply modified. So of course, here also instead of returning S, right, you return a 1 by 1 matrix with the diagonal entry as a 0. Right? So fine, you are able to visualize this. Right? So what is the running time of this algorithm? Number of vertex by multiplied by is it v square? So the analysis is a very nice analysis. So v multiplied by is correct. So why is that? How many levels of how many recursive calls are there? As many recursive calls as the number of vertices. That is clear. How do you account for the work, right, in every level of recursion? It is summation of di. Running time is n multiplied by summation of di. Because you see what you do in every step, in every recursion call, what do? You go to di entries, right, and you reduce the values by 1. Right? How many times will one value reduce? If it is starting at d1, eventually it will come to d0. Eventually it will come to 0. Right? Therefore, the total time taken, right, accounted in this particular way, right, is right. So this is an upper bound. This is correct, but this is a weak upper bound. What do? You say that it is n. At every step, your answer is actually a weaker bound, right? So you are saying that it is n into n, right? Because in every, there are n recursions, and in every recursion you have at most n amount of work. So it is n square. But you observe that I am going to count the running time in a very different way. I am claiming that the running time is actually summation di. Why is it summation di? You start off with d1, d2 to dn. Right? As the algorithm runs, in every recursion, the degree keeps reducing by at most 1. Some of them it reduces by 1, some of them it does not reduce at all. But eventually the degree of every vertex comes down to 0. Right? So therefore, the algorithm actually runs in at most summation di time. Right? The total amount of effort that is involved is just summation di, right? Which could potentially be smaller than n square. For example, if you take planar graphs or if you take trees, summation di is just 2 times n minus 1 or 3 times n minus 1. Therefore, this is a better analysis. Right? So, the reason for showing this in the recursion is to convince you that understanding the underlying graph theory helps you to do a better analysis of the associated algorithm. Fine. I leave you with one more question. Can we write a formula for this? Or can we get an algorithm to print the number out? Currently I showed you how to first answer yes. Then I showed you how to modify the program to print out one graph. Right? Now I am asking you to print out that number of graphs which are there of degree d1, d2 to dn. Right? So we will also visit this during the course. So there is a formula, right, and you can implement that particular formula. So now let us start a new thread, right, which is related to what Meghna has done. Right. So she explained to you DFS, right, in undirected graphs. I am going to introduce a graph theoretic problem to you which can be solved very efficiently using DFS in directed graphs. I won't show you DFS in directed graphs, but I will show you a inefficient solution for that particular problem. Okay? So this problem is called ranking It's a very interesting problem. We are going to consider a significantly simplified version of this problem. Right? So let us assume that there are n players, right? And you have player 1 is strictly worse than player 2. Okay, first rank player is always better. So let us change the direction. The first rank player is strictly better than player 2, who is strictly better than player 3, and so on, strictly better than player P. Okay. The restricted or the simplified case that we are going to study now is the case that when player I and player J play the game, whatever game it is, imagine it is tennis or something, the better player will always win. Right? So, given the result some number of games played as input. So, what is given to you? What is given to you is that player 1 played player 2 and obviously player 2 lost. Player 2 played player 3, right, and player 3 lost. Of course, this is all the data that is given to your program. You don't know this. Right? How many rankings are there which are consistent with the given information? The given information is this. How many rankings are there given that P1 has defeated P2 and P2 has defeated P3? Do you know the relationship between P1 and P3 in the total ranking because of seeing these two games? See, what is the model in the problem? The problem is that the players are ranked. Whenever they play, the better player will always win. What you can see is that only the result of the outcome of the games, you don't know the global ranking among all the NC2 pairs, right? But you see only some pairs. You see P1 and P2 play, you say, oh, P1 is better than P2. Then you see P2 beat P3. Then you know P2 is better than P3. Should P1 and P3 play, or you already have the information? You already have the information. So therefore, there is a unique ranking here where P1 is better than P2, which is better than P3, that you can print out immediately. just by playing only 2 games of the possible 3 games. Let us do this when there are 4 players, right? So, P1 plays P2, beats him. Then P1 plays P3, beats him. Then P1 plays P4 and beats him. Fine. Now do you know what the relationship between the 4 players is? You know that P1 is a king, right? You know that P1 is the best player. So now this question is about coming up with a ranking such that the ranking is consistent with the observed data. I don't want the exact answer with respect to this given information. This obviously you are not giving me enough information. So this sort of a ranking can be done by an algorithm called, have you studied this? Okay, so you must have studied, or some of you might have seen this problem called topological sorting. Where you are given what the textbooks will tell you is a directed acyclic graph. Directed acyclic graph. Directed means there is a strict winning relationship. Acyclic means there is no cyclic defeating pattern. Right? P1 defeats P2, P2 defeats P3, P3 defeats P1, does not happen. Such a graph is given to you. Once such a graph is given to you, you must arrange the players in a linear order consistent with the given observation. This is called topological sorting. Fine. Right? So therefore, what is the algorithm design exercise? Right? So input consists of a directed acyclic graph. What is the output that you should give me? A linear ordering you must give me a linear ordering consistent with a DAG. I hope you understand what a linear ordering means, right? You are going to order the players as the vertices of the graph as P1 before P2 before Pn. You are going to output that. If Pi before Pj, then in the DAG the edge is from Pi to Pj. Right? That is what you are going to output. Fine? Clear? Alright. Any ideas to solve this problem? I hope the problem is clear. The whole problem is here. This is all the motivation. The problem is that input is a DAG. You must output a linear ordering consistent with the input DAG. Consistent meaning that if Pi before Pj, see, for example, let me go to the next page. For this DAG, P1, multiple outputs are possible. P1 is definitely the first because P1 has defeated all of them. Then I can output anything that I want. that is a legal, valid answer. But you must ensure that, see, P1 is before P3, right? P1 is before P2 in the graph, right? So the edge is oriented in the correct direction. Look at P2, P5. P2 is before P5, but the edge doesn't even exist in the graph. That is legal, that is okay for me. Therefore, the partial order, the linear order, must respect the edges given in the DAG. Must respect means that if in the DAG P1 is oriented to P5, then P1 must occur before P5 in the linear order. Right? If P1 has defeated P5 in the game, in the tournament, then P1 should be ranked better than P5 in my output. It can't be after. This is what I mean by consistent. How are you going to do this? No, I have not talked about DFS yet. So DFS, we will present DFS and show you how to solve this with DFS, but I want a simpler algorithm. Correct. I wanted to bring in the degree concept in directed graphs. Right? Because it is a DAG, there is a vertex whose in degree is equal to 0. Right? So main observation, in a DAG, so because it is directed, right, the graph has two types of degrees, in degree and out degree, edges, number of edges coming in and number of edges going out. Okay. Now let us just see this. I am saying I have a DAG and you are telling me that in that DAG there is no vertex of in degree 0, right? So which means what? Sorry, you will be able to find a cycle, right? If there is no vertex of in degree 0, then every vertex has an edge coming in from somewhere, right? So therefore, if you keep going to unvisited vertices, which is what DFS does, you start to complete the proof of this argument, you start at an arbitrary vertex, keep going to a new vertex, V1, then you go to V2. Like this you go, there are only finite number of vertices. Some point of time you have to repeat a vertex, right? If you argue that there is no vertex of degree 0, that is, if V does not have degree 0, at some point of time you should either turn like this and come back, you will get a back edge in your DFS, or you will come back to this place, which is a contradiction that the graph is a DAG. Therefore, there must be a vertex of degree 0. Now time has come for me to stop. So here is the algorithm. First, output all vertices of in whatever order you want. First, output all the vertices of in degree equal to 0 in whatever order you want, right? Then remove them. Reduce degrees. Repeat. Okay. So this ordering is a valid output. just to convince you that this is very easy to work with, imagine a tournament in which everybody is played everybody else, right? Which means that there will be one winner, remove that person. Then the second person you will list, then the third person you will list, right? So I am done. So you just output people in layers, right? This is the first rank people who have not been defeated by anyone, remove them. Then output the second rank people, right, who have been defeated only by the first rank people, right, and so on, output them in whatever order. This respects the whole given information. Right? We will see a much better algorithm which is faster, right. I leave you, because I am out of time, I leave you with a third question: how much running time does this simple algorithm take? We will discuss this again at 4 o'clock. Right? So anyway, you guys will be here around 2:30. So I will come around and we can discuss it at that time also.